So today what we will do, we will go over proving some of the problems to be NP complete. So the first choice for this problem is called the clique problem. So what we are covering today is some NP complete problems. Okay, so what we will first see is the clique problem. So before I tell you what is a clique, let me first define some term. WF is a subgraph of a graph VE if this condition is satisfied, that W is a subset of V and F is a subset of E. Then we call this is a subgraph of this one. Now a clique of the graph VE is a subgraph or is a subset W of V, so that the graph W and W choose 2. When I write W choose 2, it means this is the graph made out of all possible edges between the vertices in V. So this is a complete graph with the vertices in W. That's what it means. So a clique is a subset of vertices W, so that this complete graph is a subgraph of V. So basically clique is a subset of vertices of the graph where between these vertices all possible edges are present. Then it's called a clique. Now the language version or the decision version of this problem will be, given a graph, we'll be asking, does the graph has a clique of size k? So the clique problem is this. So instance of the clique problem is a undirected graph VE and an integer k. Question is there a clique with k vertices? So this is the problem. Given the graph, you are asking whether there exists k vertices which form a clique in the graph. And we will show that this problem is NP complete. Okay. So for this one, as we know, first thing we have to show that this problem is in NP. So first step is to show that the clique is in NP. How do you show that clique is in NP? What is the certificate? What is the certificate of this problem? What is the certificate of this problem? A clique. So given the graph V and a clique of it, that will be a certificate of the graph for this problem. So given the graph and a clique of the graph, that is a certificate. A clique, given clique is a certificate. Now one has to verify whether it is really a clique in the graph or not. So that verification can be done in polynomial time very easily, because you have been given the vertices. Only thing you have to check between any two vertices there is an edge in the graph or not. But that check can be done definitely in polynomial time. If the graph is represented with a matrix form, its per edge it takes only order 1 time. Even if it is not represented with matrix adjacency matrix, it can take only at most order n plus e time. So anyway, it is polynomial. So given a clique, you can verify whether it is a clique in the graph or not in polynomial time. So that means the problem clique is in NP. So that's the first step you have shown. So you have to write all this. So given clique given a clique of VE, it can be verified in polynomial time. So this is in NP. This is the first step. So most of the time this will be the easiest step in all the steps to show something to be NP complete. Now the next one we have to choose a known NP complete problem, and we have to reduce that problem to the clique problem. So what we will choose here is the 3CNF SAT. So we are going to show that 3CNF SAT is polynomial time reducible to clique problem. This is what we will show, and we already know that 3CNF SAT is NP complete. By showing this, we will show that clique is also in NP complete. Now we have to go back and see the definition. What does it mean that this is polynomial time reducible to clique? What do we have to show? That each instance of 3CNF SAT can be mapped to an instance of clique by a polynomial time transformation. Then first step is that, then you have to show if clique has a solution, then this has a solution. If this has a solution, corresponding transformation has a solution. If and only if. Once you show that, and all this solution can be done in polynomial time, everything can be done in polynomial time. If you can show, you are done. So let us see. So I am going to take one instance of 3CNF SAT, and I will tell you what is the transformation we are going to use to transform that problem to an instance of a clique problem. So remember, we are going to map the Boolean formula to a graph. So let's see, what do we do? So let us see what is the generic form of a 3CNF SAT. If you remember, it is AND of clauses like this. Certain clauses, say there are k clauses. So there are k such clauses, 1, 2, 3, 4, like this, all clauses. They are connected by AND. Now within each one of them there are 3 literals. So let us see, for each literal we construct a node, like say x1. x1 can appear here, appear here, but x1 has only a node in the graph. So each node represent one literal in the graph. Now how do we connect two nodes? We connect two nodes if their corresponding literals appear in different clauses and they are not negation of the other. So suppose x1 is here and somewhere is x1 bar, then we will not connect x1 with this x1 bar. So first of all, for each literal, each copy of the literal, each literal here I have a node. So if there are 3, each one has 3 literals, so there will be 3k nodes. Each copy has a node, suppose. Each literal has a node here. Now we connect two nodes, say this one say x1 and this one say x2. If x1 and x2 appear in two different clauses and they are not one is not the negation of the other, then we connect. You just put another node. For each literal there is a node. If they appear, yes, in different clauses is fine. Okay, so that's the graph we are going to form. Now the claim is, if this, so this is the transformation, and this transformation can be computed in polynomial time, definitely. Now the claim is, if this 3CNF SAT has a solution, then this has a clique of size k, and if this has a clique size k, this has a solution. So let us see why. If this formula has a solution, if there is a truth assignment of the variables, what does it mean? At least one clause of one literal in each clause must be true, because it's a AND. So each clause individually must be true for that truth assignment. So at least one here, one here, one here, everywhere has to be true. Now go back to those corresponding nodes here. Those nodes cannot be negation of one is a negation of the other, because if this is true, the negation must be false. That cannot give you true. So if all of them are true, that must be the case that one is not the negation of any one of them. What does it mean? This k node must form a clique in this graph. Every possible pair of all this must form a clique. They must be connected. So there is a clique of size k. So I am showing by this argument from this one to this direction, from the formula to the graph. What I just told you or proved to you, that if this formula has a solution or has a truth assignment, then this graph has a clique of size k. Now in the reverse direction, I am going to tell you, if this graph has a clique of size k, if this graph has a clique of size k, then those k nodes must appear in k different clauses, because edges only connect nodes from different clauses, and they cannot be, again, one cannot be negation of the other. So it must be true that all these k nodes must be true, should be able, I can assign the variables simultaneously a value such that all of them are true, because nobody is negation of the other. So what you have shown by this construction, first of all, this is a polynomial time construction, and if 3CNF SAT instance is satisfiable if and only if the constructed graph has a clique of size k. So this is the transformation and this is the proof. See, when we took the transformation, we had this one in mind, that this is the way the proof will proceed. That's why it was constructed like this. We put the edges between the nodes of different clauses, that enforces that if there is a k clique size, basically all those k nodes must come from different nodes, different clauses. That ensures that, so that every clause is true by that. And why did we take the other condition, that nobody can be in the negation of the other? It means those any two nodes connected can be assigned a truth value simultaneously. That has to be true also for making this Boolean formula to be true. At least one variable from each clause has to be true simultaneously. If one is the negation of the other, you cannot do this. And that's why these two conditions ensure that if this has a clique of size k, this formula is satisfiable. And this is the way you should show the reduction to prove something is NP complete. So this is an example. So now let us see. Now I will move to another problem. So now at least we know one more problem which is NP complete, the clique problem. So let us consider another problem which is called the independent set problem. What is the independent set problem? It is again, the instance problem is this. undirected graph VE and an integer k. Question is this: are there k pairwise non-adjacent vertices? What do you mean by this? This k vertices cannot have any edge among them. Non-adjacent means two vertices are non-adjacent means they do not have an edge between them. So we are asking, given the graph and a k, are there k vertices such that no two vertices in that set are connected? That's why they are called independent. They are not connected. So this is another problem which is called the independent set problem. Now we are going to show that this problem is also NP complete. Can somebody tell me what should be the natural choice of an NP complete problem which can be reduced to this? Clique will be, how can you reduce? Yes, very good. So how can you reduce clique problem to this problem? Yes, very good. Yes, that's it. That is the reduction. So what you do, you take the graph VE, a independent set, k vertices are independent if and only if they form a clique in the complement graph. What is a complement graph? Given the graph, you take the graph with same nodes, but the edges will be those edges which are not present in the graph. That is the complement graph. So now the trick is, you take an independent set in this given graph that will form a clique in the complement graph. It has to be, and is vice versa, and that is the transformation. So first of all, let us see again. Let us go step by step. Step 1, we have to show that this problem is in NP. How do you show it is in NP? What is a certificate for this problem? Given k vertices, which is an independent set, that's a certificate. It's an independent set of k vertices is a certificate. And given this, you can verify this is an independent set in polynomial time. What do you have to check? You have to check any pair of vertices in that set and check there is no edge in the graph between any pair of them. So this is in polynomial time verifiable. So certificate in this case is an independent set of size k. So this is the certificate, and this can be verified in polynomial time. So this is the first thing. So this is in NP. So this shows that the problem ISP in the independent set problem is in NP. Now the next step is the reduction, and somebody has already pointed out the reduction. So what is the reduction? Observe, so this is the reduction. Observe, W is an independent set in the given graph VE if and only if it is a clique in the graph, complement graph. What is complement graph? Same nodes, but you take the V choose 2, that is the all possible edges minus the edges of given graph. That is the complement graph. That is the notation. So V choose 2 is the set of all possible edges among V vertices. You have taken out all the edges which are present, so that will form the complement graph. So the claim is this: the W is an independent set here if W is a clique here, and if W is a clique here, they form an independent set here. How do you prove this? The proof is very simple. Because if W is an independent set here, any pair of vertex does not have edge here in that set. But in the that means by definition in the complement set any pair of vertices has an edge there. So that means they form a clique here. And the logic is just the opposite to show that if this is a clique, this is an independent set here. So a simple example, let me take a simple example for those who are still confused. So let's take this example. This is the graph VE. So what is the complement graph? Complement graph will be this, say this. I think that's it. This is the complement graph of this graph. Now, there is a clique here, say these three form a clique. Look at this, these three form an independent set here. And these three form an independent set here, this forms a clique here. So this gives us the transformation. So given the graph, you transform it, the transformation is just to create the complement graph. But that can be done again in polynomial time. So transformation is polynomial. And if this has a solution, this has a solution. I have shown you by this property if and only if. So the reduction is polynomial. So independent set problem is NP complete. Because we have already shown the clique problem is NP complete. So this is the second example. Now let me take a third example. Third example is called the vertex cover problem. So the vertex cover problem is this. The instance is, okay, before I tell you this, let me define. A subset of vertices W is a vertex cover of VE if any edge AB, if you take any edge AB from the graph that has at least a vertex in W, that's why it is called the vertex cover. It is as if these vertices are covering all edges. You take any edge AB from the graph, its intersection with the set W must be non-empty. So for every edge, AB given in E, a set of vertices are called vertex cover if all the edges of the graph has at least one vertex in that set. That is called a vertex cover. Why is it called vertex cover? Because as if this set of vertices are covering all the edges of the graph. It's touching all the edges of the graph. Okay. Then what is the instance of the problem? The instance of the problem is this. Given the undirected graph again, V and an integer K, the question is, is there a vertex cover of size K? So this is the vertex cover problem. So you are asking whether there exists a vertex cover of size K. Okay. Now tell me, first of all, we have to prove it is in NP. What is the certificate of this problem? A vertex cover. Certificate of this problem is a vertex cover, and you can check, given a vertex cover, you can check it is a vertex cover of the graph in polynomial time. Right? What do you do for this checking? Take the set of vertices, check every edge and check whether at least one of the vertices of that edge is present in the given vertex set. That is a check, and that can be done in polynomial time. So certificate again is a vertex cover of a graph which can be verifiable in polynomial time. And how? I just told you. So this is in NP. So the problem is in NP, that the vertex cover VC is in NP. Now comes the difficult part, step 2. First of all, we have to choose one problem from known NP complete problem. So which one you will choose here? Sorry?
Minus k vertices are independent set.
Very good. So he has told you the solution. Observe this. This is the observation. If W is a vertex cover of the given graph, then V minus W is an independent set. It just follows from the definition. So the claim is W is a vertex cover of V, then V minus W is an independent set and vice versa. Why is that so? If W is a vertex cover of the given graph, take the rest of the vertices which are not in W. So take a vertex from V minus W. I am claiming any two of these vertices cannot have an edge between them, because if that has an edge between them, then that edge is not covered by the vertices in W. But you said W is a vertex cover. That cannot happen. You take any two vertices from V minus W. My claim is any two vertices from V minus W cannot have an edge between them, because if there exists an edge between them, then that edge will not be covered by a vertex in W. But W is a vertex cover you have taken. And vice versa. The logic is just the opposite in the other direction. And that's why this is true. So what is the instance? What is the mapping of the instance? So given the graph, this time the transformation is almost immediate. You retain the graph itself, you don't change anything. But the question of k vertex cover, you will be asking, that will be mapped to a question of n minus k independent set. So take an instance of vertex cover, take an instance of independent set which we know to be NP complete, map it to, so suppose this is an instance of independent set, ISP, independent set problem. So suppose that there is this k. Now this has an independent set of size k if and only if this vertex cover VC has a vertex cover of n minus k. So n minus k vertex cover here k independent set, and this is if and only if. So this transformation is automatic, is polynomial, and if this has a solution, this has a solution. If this has a solution, this has a solution. So this problem of vertex cover is also NP complete, because we have reduced an NP complete problem to the vertex cover problem. So every time you can see this problem reduction only requires a little bit of tricks. You really need to know, or need to come up with a proper problem to reduce to it. If you try to prove this vertex cover by something else, it will be lot difficult. I am not saying you wouldn't be able to do. But probably 3 CNF SAT you can probably will be able to do it, but it will take a lot of your effort and energy. But this from this reduction to this reduction is almost immediate. So let me take another problem now, which is the Ham cycle problem. And I will not give you a reduction for the Ham cycle problem. Actually, it can be shown from the 3 CNF SAT that the Ham cycle is also NP complete. So let us know that Ham cycle problem is NP complete. I will not give you the reduction because that reduction is not very straightforward. It's a little bit technical, and I am referring you to the text to see the reduction. It has been given in the text. Undirected graph VE, question, is VE Hamiltonian? What is an Hamiltonian? Hamiltonian cycle, if you remember, is a cycle which goes over each vertex exactly once. That is a Hamiltonian cycle. So given the graph, we are asking whether it has a Hamiltonian cycle or not. So 3 CNF SAT can be reduced to this problem. I refer you to text to see the reduction. That will be a good exercise for you to know how reductions work. So let us know that this is an NP complete problem. But let me tell you why from this one we can deduce that another problem is also NP complete, and this problem is quite practical. This is called the traveling salesman problem, or TSP, traveling salesman problem. What it is asking? It is asking, the instance is this: a weighted graph, weighted undirected graph, but this time a complete graph, weighted undirected complete graph. V, the H set is V choose 2 and W is the weight, and an integer k question. The question is this: is there a tour? What is a tour? Tour is basically something like a Hamiltonian cycle. Tour is a cycle which will visit each vertex exactly once. That is a tour. That's called a tour. So is there a tour of total edge length, or edge weight, not length, edge weight k? So that's the question. So this time the graph is a complete graph, and we are asking, is there a complete tour or a cycle which goes over each vertex exactly once, where total weight is exactly k? Why is it called traveling salesman problem? Let me tell you a little bit about this. This problem came from this practical situation. There are lots of cities. One salesman has to traverse all the cities. One salesman has to traverse all the cities, and suppose all the cities are pairwise connected by some roads. So traveling from one to the other city, there are some costs associated with it. I don't know. I have not drawn all the possible ones. So each edge represent the cost from, say, from this one to this one. This edge will represent the cost to go there. Maybe it is the length of the road, or maybe something else. So the goal is the salesman will go over all the cities to sell his product, and such that he wants to do it in a thrifty manner, so that it does not cost him too much. So he wants to travel all the cities exactly once, so that the total weight or total cost is as little as possible. That's why it is called the traveling salesman problem. The decision version is this. So basically we are taking a graph which is a complete graph, but each edge has a weight. We are looking for a tour of all the nodes, of visiting each node exactly once, where the total edge weight will be k. That is, for decision version we have to introduce the value k. So now let us see, first of all let us see what is the certificate of this. Given a tour of size k, a tour of weight k, and you can verify it is a tour of weight k in the given graph in polynomial time. And that is, so this problem is in, so TSP is in, first one is TSP is in NP. You have to write all this logic. Next one is to choose a right problem for this, so that you can reduce that given problem, given NP, known NP complete problem to this problem. Can somebody suggest me that which one of the problems you know that will be reducible to this? Ham cycle. So this time probably Ham cycle is the right choice, because Ham cycle also has a notion of tour. But now the problem is how to map this tour concept of a Ham cycle to the tour concept of this traveling salesman problem. Because Ham cycle did not have any edge weights, and it was not a complete graph necessarily. So is there any suggestion? Somebody can tell me what are the transformation you will be using? Transformation is really simple. It's only one trick, nothing else. Okay, so let me tell you. What you do, given the graph G, first of all, you make this graph complete, say G prime. So this is a complete graph. Whichever edge was not present, you make them present here. Not only that, what you do on these new introduced edges, you put a weight very high, more than k. You put the edge weights of those new introduced edges to be very high, more than k. Now it should be clear, why did I do this? If there is a Ham cycle here, definitely this is also a tour of. Okay, so not only you put, I have to introduce the k here. So here your k will be nothing but n. What you do, for each edge here, you put a weight 1 on those edges, and those edges which are not present in G prime, you put a edge weight very high. So now if there is a Ham cycle here, there is a tour of size n, because there are n vertices. So n vertices means that Ham cycle has how many edges? N edges, and those edges are also present. Their edge weight will be n, and put on the other edges, say edge weight more than n. So what does it mean? In the reverse direction, if this has a tour of size n, that must be going through the edges of this graph, because all the other edges, if it takes, its total edge weight will be more than n. You have retained all the edges of G in this graph with edge weight 1, and for all the new edges you have introduced here, you have put a weight very high, more than n. So if it has a tour of size n, that must be going through the edges of this graph only, because if it takes any edge which are not present, any one edge is more than n, that is not possible. So if this has a tour of size n, this has a Ham cycle of size n, not size n, this has a Ham cycle, and if this has a Ham cycle, definitely this has a tour of n. So you have reduced the problem to the one to the other. So this is the reduction. Again, the reduction is polynomial. For all the edges which are present in G, we have put the edge weight as 1, and all the edges which are not present in G, we have put an edge weight more than n.
Given a problem, different edges have different weights.
No, sorry. What you are doing, you are mistaking the direction again. We are reducing the Ham cycle. This is the Ham cycle problem. We have to take an instance of the Ham cycle, transform into the instance of the tour True problem where different weights. We are not taking an instance here and transforming here. So don't get confused with the direction. Because this is known to be NP complete to us, we are going to prove this is to be NP complete. So we are reducing this one instance to a particular instance of this. It need not be all edge weights are different. So this is a valid transformation, and that's why it is working. So let me complete here, and this completes also NP completeness.